not all.
How was that
It
fire
wouldn't
drill?
have been that exciting. How what?
How was that fire drill?
How was that fire
Who was
drill?
on there? Who was on what?
You didn't even know about it.
I don't know. I didn't know it was going to happen, and all of a sudden it happened, so we just walked outside. I thought it was kind of funny because there were still kids walking up to check in with me, and they said, all clear, we can all go back in. Oh, where that goes. I figure this is just working, even though it doesn't act like it is. So, you know, where we got to with that, I guess you gotta look at the video. So if you're traveling, I need to see that 12.5B sometime real soon. Before I see you Wednesday, I need to see that. If you were here, you're okay, because we looked at it a lot. And we talked about it even more. And the next test that you have will have just no more than 2 pages of problems like that on it. Some of those are harsh. They're really nasty. Maybe some of the rest of this will make a little bit more sense to you.
Back to triangles.
Yeah, back to triangles. Let's keep it simple, right? See, everything gets to be made up from triangles. That's why they spend so much time with triangles. And even circles. The relationship along the circle goes back to triangles. Have you seen that yet? What's the equation of a circle? Yeah? And all the h and the k are is how much we shift them away from the origin. If we put them on the origin, that's the equation of a circle. What is that? What's the formula? A squared plus b squared equals c squared. Isn't that Pythagorean? Yeah. So everywhere that we draw a circle, it's just triangles. It's all triangles. That's all it is. It's an infinite number of triangles. So in math, we spend a lot of time with triangles. Because eventually when we work with a curve, that little section of the curve might be a section of an imaginary circle. And if we study this little section of the curve, we're studying a little section of the circle. Really little. Smaller than you can visually see. But you see in nature, nothing behaves like this in a straight line. Nothing is linear. Everything is curved. So eventually your math has to get to a point where we get to study curves. And we equate those curves with itsy little sections of a circle. And then we study what's happening as that line curves. That's how we can apply math to really complicated stuff. So we're getting there. Eventually we'll get away from just crunching numbers. Not in this class, though, but it's coming. So we spend a lot of time with triangles because the relationship between the side lengths of triangles is really important. But as you well know, not all triangles are right triangles, are they? In fact, very, very few are. So we have to be able to look at triangles which are not right triangles and look at their relationships. And we'll eventually get into the relationships of how the angles all relate to one another, how you can find angles based upon side lengths, even if they're not right triangles, how you can come up with side lengths if you know angles. All of that is coming. But first off, a little bit of similarity. Side, side, side similarity. So I'm just gonna go right to the book. I think it's gonna be relatively straightforward to you. I just wanna show you a couple of tricks with these different relationships that we can look at. So if we have two triangles that are similar to one another, that means they're the same shape, but they're not necessarily the same size. As a result of having the same shape, and we've done this a whole bunch with size change factors and things like that. Working with reflections, we get congruent. Working with rotations, we end up with congruent, but those are also similar. Anything that's congruent is also similar. But if we were to have a couple of triangles, so they give one here which is called G, and there's F and there's a D point, and they give some lengths. Of course, they have to make one of them a fraction to make it less than straightforward. And then they have another triangle over here, which is A, B, C. And they make a statement that they're similar to one another. Remember, if they're similar, that's that single line that's squiggly. That means similar to. And what we need to do is we need to take a look at how these are similar, why they are, or take a look at them and see if they're similar, and if so, why are they? So one way you can do this, if you're just given all the side lengths, is you can take the side lengths and put them in order from least to greatest. So if I took the small triangle here, which is side length 3, 6, and 8, I can write those in order. And then I can take the side lengths of the larger triangle and write those as denominators. So 8 is the smallest, then there's 15, and then there's 64 thirds.
The 15th is 16.
Is this 16? Ooh, that would have changed the world, wouldn't it have? So this is 16? Okay. So by definition, if they are similar to one another, what's going to have to be true about all of these ratios? This is a ratio of the smallest to the largest, the smallest triangle to the largest. They've got to be equal, don't they? So is 3/8 equal to 6/16? Yeah, that's good. So then if we can just figure out whether 6/16 is equal to 8/64 thirds, then we'll know whether these are truly similar or not. So what would be a fast check for looking at these two fractions to see if they're equivalent? You could simplify the 64 thirds even without doing that. Real short. Try to keep the amount of work that you have to do down to a minimum. I know that sounds really good, right? Yeah, try to do less work. Yeah, work smarter, not harder. Yeah?
Dividing them by 2, like the 8 and the 16.
You could divide the 8 and the 16 by 2? Well, they're said to be equal. You can't do that. Mara, what do you think?
I was going to say cross multiply.
Yeah. 16 times 8, and find out if it's equal to 6 times 64 thirds. You see, this cleans up a little.
We'll just hang here for
6 over 3 is 2. So that's 128. Is that 128? Yeah. So that, they're similar. So this is the most simplified form of those three fractions, the 3/8. And what we're doing is we're comparing the smaller to the larger. And if we were to start with the larger triangle and create the smaller triangle, that's a ratio of the smaller to the larger triangle. So this is a ratio, they call it of That's a ratio of similitude. So it's kind of like a size change factor. In fact, it is a size change factor. So for example, if I wanted to know how long to make a triangle that was going to have a corresponding side to this side length of 8, we could take that 8, multiply it by the ratio of similitude, and we would get that corresponding side length. So assuming we didn't know it. For example, if we didn't know what this 8 was, we could take 16, multiply it by 3/8, and we would find, what am I doing? 16 over 8 is 2, 2 times 3 is 6. Oh, so then this side does not correspond to this, does it? Excuse me, that one, this side would correspond to that side. If you took 64ths and you multiplied it by 3/8, then you would end up with that long side 8. So we can take the ratio of similitude, and instead of working with a proportion where we're missing one of these numbers and we put in a variable for x and solve for x, we can just use the ratio of similitude to multiply a length to come up with a corresponding side length. So another problem, they give us a right triangle like this. And they ask us to find length x. So what might you do to do that, to find that value of x?
You can use the Pythagorean theorem.
You could use a Pythagorean. Yeah. And you could also do this. What's that?
The 5, 12, 13 triangle.
5, 12, 13. So we could say that this is 120 because of the Pythagorean triple, 5, 12, 13. Because 5 squared plus 12 squared is 13 squared. No differently than 50 squared plus 120 squared is equal to 130 squared. So the idea is that what we're doing is we're thinking of this as a triangle similar to the 50, the 130, and the x. And we know that each of these sides are 10 times larger, therefore that missing leg needs to be 10 times larger. And then they give us one more example where they have got a triangle that's drawn like this. It's a right triangle again. And they say that it's, what do they use, sevenths? 3 sevenths, 5 sevenths, and then they say x. So is there another similar triangle that you might be familiar with? Which would, 3, 4, 5, which would have the same ratio. Yeah, so if we had something which was 3, 4, 5, and then we took this, and everything got multiplied by 1/7. So we'd use a ratio of similitude, 1/7. 3 times 1/7, 5 times 1/7, 4 times 1/7. So this length would have to be 4/7. Here the idea is thinking of a ratio of similitude of 10. We start with a small triangle, multiply everything up by 10. So that's all I'm going to say. Let it work. So our questions 1 through 11 16 and 17 picked out.